Many differential equations cannot be, unfortunately, solved exactly analytically just by chalk or pencil and paper. Then, if we really need a solution, we must be happy with the approximate numerical solution. Approximate is a disadvantage. That means the results are not exact, they are only approximate. And numerical is another disadvantage. The results are not in the form of a formula containing some parameter. Only numerical values are possible output. But if nothing better, we must be happy with that. And perhaps the simplest numerical approximate method to solve differential equations is the Euler's method. It can be expressed, it can be explained in a very, very simple way. If you travel with 50 kilometers per hour, the speed, for 2 hours, kilometers per hour, for 2 hours, then you make 100 kilometers. In a more general setting, the distance is the speed times time. And when we have the differential equation, that derivative is some function of z and time, then the change of position, delta z, can be written as the derivative, which is the right-hand side, times the step size, say h, if we denote the step size h. That means the new value zn plus 1 is the previous value zn plus the change, which is h times a function that appears on the right hand side, evaluated at the old point zn and the old time t sub n. And similarly, the new value of time t n plus 1 is the old value of time plus the step size h. In this way, it works for one differential equation, and when we have a system of differential equations, then instead of one right-hand side, we can have two or more right-hand sides, so we can consider a vector of the right-hand sides, and similarly, z is not alone, there will be x, y, and perhaps more functions, and z is then also a vector. The time t remains scalar. And then this remains perfectly valid, just these quantities are all vectors. Time is scalar, the step size is scalar, time is scalar, and everything else, the position and the right-hand side is vector. Let us illustrate how it works with the following example. Consider the differential equation x derivative being, say, I have prepared x times y times t, and y derivative being x squared plus y minus t. We need the step size. Let's take h being 0.1. This is usually some small number. The smaller the value, the more precise the results, but the longer the time of computation. And we need some initial condition. Say x at 0 will be 1, and y at 0 will be 1 as well. And then we can prepare a table where for each index n, we will write the value of time, the value of x, the value of y, and then the right-hand side, f1, evaluated at xn, yn, tn, the value of the second right-hand side, evaluated again at xn, ymtn, and then we will multiply f1 with h and f2 with h. Then, starting with index 0, we read these three values from the initial condition. T is 0, x is 1, and y is 1. And now the computation starts. We evaluate the right-hand side of the first equation. X times y times t, 0 times 1 times 1 is 0. And we evaluate the right-hand side of the second equation. X squared is 1, plus y is 1, minus 0 is 2. So this was the main part of the computation, evaluating the right-hand sides. And then we multiply these two numbers with the chosen step size, 0.1. So we get 0 and 0.2. And now we add these changes to the previous values to get the new updated values. So for the next index, new time will be the old time 0 plus the step size. 0 plus 0.1 is 0.1. And we increment x by this value, which is 0, so 1 remains 1. And we increment y by this value. 1 plus 0.2 is 1.2. And this completes the first step, and we can go on. We can compute again by evaluating the right sides, multiplying by the step size, and adding to the previous value, and so on and so on. This can be visualized by the following graph. Xn, Yn is a point in this plane. We evaluate the vector f arrow, which is in this case 0, 2. And we move in this direction, but just a small piece, just a small step, given by this edge to this point. This is the new point, 1, 1.2. And then, again, in this new point, we evaluate the right-hand side, we get a new vector, and we move one small step in this direction, and so on. In this way, we get a system of points in the xy plane, and if the step size h was chosen reasonably small, then the sequence of these points approximate the solution, the integral curve of this differential equation. The advantage of Euler's method is that it works for any differential equation.